3-day field trip. I'm going to bed after this, I'm so tired. But thanks very much for turning up. I hope you enjoyed the field trip as well. I did. Like most field trips, if you ever have to organise one yourself, nothing goes according to plan, 100%. And you can't control the weather either. That's just the nature of the beast. But I hope you still enjoyed it and learned something as well. First thing before I talk about today's topic, if you still want a t-shirt from Neil, then he's going to be in the Earth Science Lab this afternoon. So if you can see him after about 3 p.m. if you still want to order a t-shirt. So yeah, Earth Science Lab after about 3 p.m. this afternoon. So today's lecture is going to be talking about, we finished our 3 categories of rocks. We've looked at igneous rocks, we've looked at sedimentary rocks, we've now looked at metamorphic rocks. When we were in the field, we saw quite a few what we call deformation structures. So where the rocks have been deformed after they've been formed, okay? And this is what we're going to talk about today, is deformation processes of existing rocks. So basically, back in time, when geologists were trying to understand Earth materials, they were trying to figure out how different rocks were formed in order to figure out about our Earth's past. They already learned quite a lot about sedimentary rocks. They observed sediments forming on the Earth's surface, collecting in layers, being buried. They looked at existing sedimentary rocks in cliff tops. They observed volcanoes. They observed how magma was cooling to form these microscopic crystals. But they were still quite confused about some of the structures they saw in the landscape. So they were confused by why we saw sedimentary rocks, which we knew form in horizontal layers initially, because they're formed from the accumulation of material on the sea or a riverbed or underneath the atmosphere. So why then, how then, they form these really weird folded structures? And also, how can we see some nice sedimentary layers here, completely cut through the middle, and the sedimentary layers have moved along that fracture? And it wasn't really until we started understanding more about plate tectonics, because remember, before the 1960s, we didn't really know or fully believe the idea that the Earth was made up of these series of plates, or the outer shell of the Earth, the lithosphere, was made up of a series of these plates that are either colliding in places, they're moving apart in other places, moving past each other in other places, or moving apart. So it wasn't really until the 1960s that we understood the idea that because the lithospheric plates were moving about on the outside of the Earth, there was a lot of pressure building up at certain parts of the Earth. So at these plate boundaries, so our plates are either moving apart, they're moving past each other, or they're colliding, we have a lot of forces building up, a lot of stresses rather. So stress, when we talk about stress, it's force per unit area. So we have a lot of stress building up at these plate boundaries. As with any natural system, the stress isn't just concentrated at the actual plate boundary, it's spread out over the area around that plate boundary. And within that area, the way the rock or the crust responds to those stress depends on the stresses involved, it depends on the rocks involved, and it can produce some really, really spectacular features on the Earth's surface. So the two main deformation features I'll talk a little bit about this week are folding. So this is where we have layers, typically sedimentary layers in the rock record, that due to the buildup of stress and the response of those rocks to that stress, we end up folding the sedimentary layers, literally like you would fold a piece of cloth. So you have a piece of cloth, and you push it on one end, and it forms these nice folds. It's exactly the same with sedimentary rocks, it just takes a lot longer. And you can see some really spectacular examples here. And these folds can occur on many different scales. This is a huge fold here, exposed in a mountain chain. You can get them on centimetre or millimetre scale as well. You can get them even bigger than this, where a single fold is hundreds of kilometres wide. but they produce often quite beautiful structures on the Earth's surface, in my humble opinion. And the other deformation feature we'll talk about today is faulting. So this is where the rocks fracture in response to these stresses building up, and there is movement either side of this rock fracture. And again, these can happen on many different scales. You can see microfaults. If you walk up Lathala Bay Road and you look at the outcrops of Subermal, you'll see quite a lot of microfaults, where there's literally been a few centimetres of displacement either side. You also see huge faults. I don't have any pictures of some giant faults, but literally there's hundreds of kilometres of displacement along these faults. Here are some nice examples of sedimentary layers that have been cut by a fault and moved away from where they originally sat. This is a road cut which has exposed numerous faults. There's one fault there, and there are other faults all the way through that exposure. And here's a nice example here. And this is a field in California which happens to lie around the San Andreas fault, which is a strike-slip fault. And you can see a really nice simple fault here, which is this basically grows of vegetation growing in the field. So when I talk about stress, what I'm talking about is force per unit area. When I talk about deformation or strain, it's basically the response of that material to the stress. So it's the change in shape, change in size of an object in response to that stress. So that's what I mean by those terms. And I'll use them interchangeably, deformation or strain, and they mean pretty much the same thing. So basically, the type of deformation depends on lots of things. It depends mainly on the type of force, the type of stress involved. And these are the three main types we'll talk about. We either refer to compressional forces, so this is obviously where rocks are being squeezed together, the movement is pushing that rock together. So these are typical of plate boundaries where we have two plates colliding, so convergent plate boundaries. We have tensional forces. This is where the rocks are being pulled apart and stretched. These are typical, obviously, of plate boundaries where the plates are being pulled apart. And we also have shearing forces, which is where part of the Earth's crust is being moved in a different direction to the other part of the Earth's crust. And that diagram nicely illustrates some of the different forces that we're going to talk about here today. So basically, when early geologists were trying to figure out how the Earth responds to the stresses within it, they did all these lab experiments. So a lot of engineers do experiments to see how different materials, whether it's concrete, whether it's a different type of alloy, respond to stresses in the real world. So they use these big hydraulic rams, which allow you to place a material in the ram and mess around with different pressures and stresses to see how it responds. Because obviously, if you want to build a building, you don't want something that's going to break in an earthquake, etc., etc. So geologists started using these big hydraulic rams, and they put different materials in there, different rock types, and they subjected the different rocks to different types of pressure. So they messed around with confining pressure. You remember that type of pressure which is equal in all directions, and that pressure increases with depth in the Earth's crust. Remember the term directed pressure. This is where pressure is greater in one direction, and is typical of convergent plate boundaries, where, as well as confining pressure, you have the pressure from the plates colliding in one direction. The geologists played around with rocks. This is just a very small example of a hydraulic ram. They're much bigger, the ones that the geologists used in the past. And just to give you a brief background to strain and different strain types. So elastic strain or deformation is where a material, so a rock or whatever it is, responds to the strain by changing its shape or size, but then when you remove that stress, it goes back to its original shape. Okay? And that's, if you're plotting stress, so this is the force per unit area, this is how the material responds. The elastic region, this is the first part of the curve, but if you take that stress away, it comes back. So the next style of deformation, which comes next as you continue to apply stress, is called ductile deformation. So this is where you change the shape or the size of that material, but if you take that stress away, it doesn't return back to its original shape or size. But actually at this stage, there is no fracturing, there's no breaking at all. The material is just gradually changing its shape according to the stresses applied. But what might happen eventually, if there's enough stress or enough strain, that material will break, and we call that brittle deformation. So this is where the material fractures, and this is obviously irreversible. So if you plot it on a graph, it's up here where it says rupture stress, where that material breaks. And this graph will look very, very different according to the material present, the surrounding conditions, so what confining pressure there is, what directive pressure there is, etc., etc. Some material doesn't even go through a ductile deformation stage, it just breaks as soon as it goes past that elastic region. This is just some background. So basically, this is a nice example of one of the very early experiments with rocks using these hydraulic rams. So this is a nice column of marble, so our metamorphosed limestone. And where they subjected that marble to very high directed stress, so like a convergent boundary, but low confining stress, so we're talking shallow depths in the Earth's crust, we saw brittle deformation. The geologists saw brittle deformation. There's evidence of slight ductile deformation, you see where it's changed the shape, but we see this rupture of the material. However, if we simulate deep depths in the crust, still with a high directed stress, but much higher confining pressure, we don't see that brittle deformation, we see ductile deformation. So the deeper you go in the earth, the more likely you are to get ductile deformation rather than brittle deformation. So the higher the confining pressure, the more likely you're going to get ductile deformation. Whereas in the shallow crust, you're more likely to get brittle deformation. And they changed the conditions, they changed the rock types, they found that actually the hotter the rocks are, the more likely they are to deform ductilely. That's not a word, I just made it up. Ductilely than they were to deform brittly, which conforms to the idea that the deeper you are in the crust, the more likely you're going to experience ductile deformation. And there were lots of other factors, so to summarize these, at shallower depth, the rock is more likely to deform brittly, as I've just shown you. The hotter the rock is, the more likely it is to form in a ductile manner. Obviously, it depends on the rock type. So sedimentary rocks are slightly more likely, particularly if they're young and still quite soft, to form in a ductile way, whereas igneous rocks and metamorphic rocks quite often break more brittly, if you were to compare the two. The rate of the application of force is important. If you very quickly apply a force, you're more likely to fracture that rock than deform it in a ductile fashion. But if that force is applied over time, you're more likely to get ductile deformation. And also, weirdly, there should be a V here, and I suppose you can imagine this with some plasticine. For some reason, if you compress the plasticine, you squeeze it together, and then you pull it apart, it's more likely to deform brittly under tension than it is under compression. So in places where you're pulling the plates apart, you're stretching the rocks apart, there's more likely to be brittle deformation. And that top box in the top corner just explains, of course, with a hydraulic ram, we can't exactly simulate conditions 100 kilometers in the Earth's crust. But at least by plotting these graphs and understanding how different variables like temperature, pressure, rock composition control the style of deformation, we can begin to understand some of the formations we see in the real world. So where materials on the Earth experience ductile deformation, we can produce certain features. So I'll start from this end. So where we have our shear forces. So this is where part of the crust is being moved in a different direction to the other part of the crust. Where we have ductile deformation, we get this form of deformation called shearing, or we get these nice bendy structures in our earth. And this is a crystal that's in the middle of a shear zone, so different parts are being pulled in different directions, and we've ended up with this strange feature. I'm not going to talk about this too much, to be honest. Where we have tensional stress, and we've got ductile deformation, we get thinning of the crust. And this actually happens when parts of the crust are being pulled apart. Remember in Africa, I told you there's that big hot spot sitting under Africa, mantle plume rising up to the surface, and it's causing the continental crust to be pulled apart. The crust is much thinner where those rocks are being, where they're under tension at that big boundary. But the most spectacular sort of expression, if you like, of ductile deformation is where we get compressional stress, and that's where we get our nice folding. Again, like I said, imagine a piece of cloth, push it up one end, and we form those nice folds. And here are some more examples as well. And they're hugely, hugely variable. Whereas if we get brittle deformation of rock materials, of earth materials, we get this faulting, and this is where we have cracks with movement either side. And we get different styles of faulting, which I'll talk about for the rest of today, depending on whether we have compressional forces, whether we have tensional forces, or whether we have shear forces. So we classify faults, first of all, in three different ways, depending on the movement of the material either side of the fault. So the first type of fault, we call it dip slip, and this is where we have a fault plane, you can see here, which is dipping in a certain direction. So dipping means tilting towards a certain direction, where the movement of the fault is up and down relative to that dip of the fault, so it's moving up and down the dip. We call it a dip slip fault. Where we have a fault which is dipping in one direction, could be vertical, could be shallow, but the movement is actually side to side at 90 degrees to that dip, we call that a strike slip fault. So this is a diagram here of a strike slip fault. This is the dip of our fault. It's actually moving laterally in relation to the dip of that fault. And the third type, because nature is not a perfect system, is where we have a bit of both. So for example, here you see there's some component of vertical motion on the fault plane relative to the dip, but we've also got a little bit of strike slip. Nature isn't a perfect system. And this is where we have a combination of shear stress and big tension as well. So strike slip faulting is formed where we have shear forces on the Earth's surface, and your dip slip faults, depending on whether you get tension or compression, form slightly different types of dip slip fault, which I'll come on to now. So where we have tension in the Earth's crust, the type of dip slip fault that we produce we call a normal fault. This is because they're more common, but I wouldn't exactly call them normal, but they're called normal faults. And just to give you a few terms that we use to describe faults, so here we have our fault plane, which is the plane along which the movement occurs. And we have some weird terms for the rocks on either side of that fault plane: footwall and hanging wall. So these terms come from old mining terminology. So basically, the hanging wall is always the side of the fault which looks to be hanging over the other one. And that's because when miners were going underground and they were digging out rocks, sometimes they'd expose the fault plane and they could literally hang their lamp off it. So that's why it's called a hanging wall. So you can imagine this side, you can imagine hanging a lamp off there. That's the hanging wall. And your footwall, the other side of the fault, which you can sort of imagine looks like a foot, which comes under the other side of the fault. So when I talk about footwall and hanging wall, that's what I'm referring to. And in a normal fault, under tension, The rocks above the fault plane, so the hanging wall, move down relative to the footwall. And overall, you can imagine, you see the sedimentary layer here, it's being pulled apart. There's actually a little gap here. This results in extension of the Earth's crust. It could be centimeters, it could be kilometers, but this type of rock forms under tension. This kind of fault forms under tension. And just an example in practice, so these are two nice examples of faults here. You can clearly see the sedimentary layers that have been truncated, they've been fractured, and moved apart. So this is our hanging wall on this side. You can imagine hanging your lamp up here. And this is our footwall on this side. You can imagine it being the shape of a foot. Our hanging wall has moved down relative to our footwall, and these beds have now been pulled apart, resulting in extension of the crust overall, and those arrows can never move the fault. So this fault must have been formed under tensional forces. So the other type of dip-slip fault formed under compression, and what happens where a part of the Earth's crust fails brittly under compression is you get a fault called a reverse fault. And in this case, the hanging wall moves up relative to the footwall. And as you can see here now, those sedimentary layers overlap. So actually, you've resulted in the length of the crust you started with being shortened. So they form under compression. So this is just a summary. If the angle of the fault plane, so the dip angle, so imagine the horizontal, and imagine your dipping fault plane, and the angle between there, we call it the dip. So the dip of the fault plane. If it's less than 45 degrees, if it's a reverse fault with an angle less than 45 degrees, we call it a thrust fault. And we separate these out just because they indicate very high pressures in compressional mountain ranges formed by a lot of compression. We can find them in other situations. In fact, the Tutu sandstone fault you saw on the last day, that was more or less a thrust fault. But you can see here, these beds now overlap. This is our footwall. It's moved down in relation to our hanging wall. And I also taught you how to measure the displacement. So from the top of the sandstone on that side to the top of the sandstone on this side is roughly 9 centimeters, I think. So that's another important term we use when we talk about faults. How much movement there's been either side of that fault. And this is just an example of showing what happens to rocks that deform under great directed pressure, so these mountain building events. You start off with some horizontal layers. You might get a bit of ductile deformation to begin with, so this folding, but eventually you might form these really nice low-angle reverse faults. And they shorten the crust quite a significant amount over time. And in terms of how these faults look on the surface, obviously if you've got a nice exposure like I've just shown you, and you can see your nice sedimentary layers inside, then you can tell it's a fault. But sometimes they can produce some spectacular scenery. So say you have a dip-slip fault like in the top right-hand corner, and one fault block has moved down relative to the other one, and this has happened quite recently. You might even see that in the landscape. So this is an example in the Middle East where this side of the fault, so here's our fault, this side has moved down, this side has moved relatively up, and you've got what we call a fault scarp. So that's a slope on the Earth's surface that actually denotes a fault plane. And this is a relatively recent fault scarp, so this movement has happened quite recently, so it's not been eroded too much. So this side has gone down, and that side has gone up. But obviously over time that will be eroded down, particularly if the movement along the fault stops, then it will even itself out. But in very young faults, we can see things like fault scarps. And just to give a bit of Fiji geology, so if anyone's ever been to the Navua River or is from around there or has done a wonderful rafting trip, expensive but worth it, through the upper Navua River, you might have noticed a fault scarp around there. So this is the upper Navua River. And actually there's evidence that this river used to flow west, east, and come out of the river delta. So it joins the river on the other side. It isn't marked on this map. However, now, at that junction, my phone is running out of battery. Okay, the junction with the Luba River, basically there's a big fault scar. So at some point in history, relatively recently, there's been movement along a fault, which has moved up to land on one side, and it actually blocked that river. So now the river has been deflected to the south, and it comes out by the sea on the coral coast. But there's evidence from sediments that that river actually flowed east in the past. So it's a really nice example. And this is just another picture of what oblique slip faulting means. This is where we've got some vertical movement as well as side to side. So finally, the other type of fault, this is the fault produced when we have shear stress. So instead of compression or tension, we've got the shear stress. So the movement is at 90 degrees to the dip of the fault. We call that a strike-slip fault. And the way we name strike-slip faults depends on which way the relative movement along the fault plane. The way you do it is if you stand facing the strike-slip fault. So imagine this line as a strike-slip fault. If you're standing on a bed here, and on the other side of the fault, the bed is seen to the right, then we call that a dextral strike-slip fault. And if you're standing on your bed on this side, and you see that on the other side the bed's moved to the left, we call that a sinistral strike-slip fault. And a lot of people instinctively say, oh, that depends which way you look at it. It doesn't actually. So here you can see, if you stand on this side, and you look at the same bed on the other side, it's moved to the left, on this side it's moved to the right. So that's how we talk about strike-slip faults, whether they're sinistral or dextral, or I've just noticed this figure called sinistral left lateral, or right lateral. Another word is sinistral, another word is dextral. So if you see those terms written in papers, that's what they refer to. And obviously a really famous example, which is actually a plate boundary, is in California. I've mentioned it numerous times. So all along the coast of California, we get this big fault called the San Andreas fault. So it's one main fault zone. It has several, obviously, micro-faults coming off it. We call them fault splays. But overall, there's one fault. You can see it here. And it's been in operation for the last 15 to 20 million years, we think. It's about 1,300 kilometers long. It penetrates to about 15 kilometers into the Earth's crust. And we think there's been about 560, 600 kilometers of displacement along that fault. And you remember from my talk about plate boundaries, Los Angeles, which is near the south, and San Francisco will one day swap places because they're on different sides of that strike-slip fault. And this diagram here really nicely illustrates a stream that once formed, but since its formation has now been offset by movement along this San Andreas fault. And unfortunately, we didn't get to go there on the field trip because it's a bit prone to flash flooding in that region. This is a really nice example. So this was a sandstone. You can see it joined up on the other side. This is a strike-slip fault. And you can see how this bed has been displaced across the surface. But that displacement isn't 560 kilometers, it's about 2 meters. But you can see that's what we would have seen if we were in the field. And just to finish off, it's going to be a short lecture today. Tomorrow we're going to start talking about faults. But actually along this fault plane, so the plane along which this movement happens, you can get some really nice features that can tell you something about the direction of movement in the past. And one feature is called a slip inside. So this is the polished surface. So obviously along the fault plane, there's a lot of friction. And actually you can polish the surface because you're constantly moving along it. And if you were to feel these slip insides, they feel smooth in one direction and rough in another. And obviously the direction in which they feel smooth, that's the direction that the other fault block moved in the past. And when we get these exposed, they can tell us a lot about previous fault line. And you can also get these grooves, also formed by friction along the slicken sides, and they're called slicken lines. And again, they can tell you something about the direction of movement. Because obviously, this is a dip slip fault, a normal fault. You can see where the lines, those slicken lines, are formed as a result of the movement. And here, these denote the movement of the fault, but obviously in a strike slip fault, they'd be moving the other way. They'd be trending the other way. And we also, because of the friction at this fault plane surface, particularly if this fault is large, we get this nice breccia forming along the plate boundary. Not always, but it's because due to the friction along the fault plane, you can break up the material actually at that boundary. And when that cements together, we call it a breccia, because it's made up of angular fragments in a finer grained matrix. But where that occurs along the fault plane, and it's formed as a result of the friction, we call it a fault plane breccia. And this is a nice example here. And sometimes, I've told you before about fluids that are constantly travelling through the earth, particularly hot fluids at depth which contain a lot of ions, and as they cool down, they precipitate out minerals. So fault planes, because they're cracks in the earth, any fluid that's underground will be flowing through those cracks. And if they precipitate their minerals, if they cool down, those fault planes can actually become mineralized. And this is a really nice example of a fault in a desert environment somewhere in the States. And along that fault plane, you have quartz minerals precipitating out from hot fluids. And because quartz is quite hard and it doesn't weather as easily as a surrounding rock, the minerals along the fault plane have actually stuck out in the land. They're actually sticking out in the landscape. They tell us exactly where that fault plane was and where those hydrothermal, geothermal fluids once travelled. So they nicely indicate where the fault plane is in this example. And another thing, because faults are essentially cracks in the earth, they can become quite easily eroded themselves. So quite often when you look around the landscape, where there's a fault present, you often get a dip in the scenery because they're more easily eroded out. So I've used the term gully. I'm not sure if that's the term you use around here, but these small creeks in the landscape quite often form when there are faults. So you might see them, this is an example here, just a cartoon, where actually erosion is taking place more rapidly than the fault is, and that's now the focus of the river. So just to finish off, I talked about cracks in the earth where there was movement either side, so that's a fault. You can actually get brittle deformation where you produce cracks but there's no movement either side. We call them joints. Now these are a bit more complicated because they can form in very, very different scenarios. They can form under compression or tension, like in a tectonic environment. But actually, just if you bury a sedimentary layer and you uplift it, so you're reducing the pressure, you can actually form cracks that way because it's allowed to expand as you reduce the confining pressure. So they're called expansion joints. You can also form joints if you have a lava flow and it cools and contracts to produce fractures. We saw columnar jointing in the field. And yes, there are lots of ways we can form these joints, but they're really, really important for geologists in industry because they might have veins running through them which contain important minerals that we want to mine out of the ground. They're really important for hydrogeology, so understanding how water is flowing underground, where we might find really nice resources of water that we can remove from the ground using wells and pumping them out in other ways. And also, these cracks often host a lot of oil. Any spaces in rocks underground can be reservoirs for oil, reservoirs for water. So people understand, try and investigate patterns of jointing quite often in terms of minerals. But remember, joints are where we don't have movement either side of the crack. So just to summarize what we've learned today, tomorrow I'll be talking about folding. So the Earth's crust is constantly being subjected to stress because of tectonic forces. We can divide these into tensional stresses, compressional stresses, or shear stresses. Types of deformation that are relevant to geology, really we can forget about elastic because we can't see evidence of that in the Earth's crust. If you apply a stress and it returns to its normal shape when you remove that stress, we're not going to see evidence of it, so that's not important to us. But we can see evidence in the rock record of ductile deformation and brittle deformation, and by studying those features we can tell the types of stresses that the Earth's crust has been subjected to in the past. And also, another reason for studying brittle deformation, which I've just been talking about, faulting, is that it's faulting that produces earthquakes. So when you get that initial fracture, that releases energy in the form of seismic waves, and that produces an earthquake. If you've got continued movement along that fault plane, it might get stuck for a while, and then when it finally moves, that releases seismic energy. So understanding patterns of faulting is really, really important for understanding earthquakes. And there are three main types of faults: dip slip, strike slip, and oblique slip. We name them the dip slip faults according to whether they've been formed by compression or tension, whereas the strike slip faults are faults that are formed by shear forces. So I hope that's clear. And tomorrow we'll be talking about faults. And go and see Neil if you want a t-shirt after around 3. Or to be honest, any time from 2 p.m. because he'll be in there with the lab anyway. So I'm sure he can help you if you go and see him after 2.